Let's take a look at a beam that is made up of wooden blocks glued together and loaded by a concentrated load P. It's quite easy for us to imagine vertical shear stresses on this beam. As you know, the average shear stress is defined as the shear load divided by the area. Well, it's important to remember that V over A is only the average shear stress. In reality, the shear stress distribution is not uniform, and the maximum shear stress will be higher than the average shear stress. Let's take a look at another beam. This is what we call uniform bending in a simply supported beam. Drawing the moment diagram, we can clearly see that the internal moment is constant from one end of the beam to the other. The beam is called to be in pure bending. What this means is, since moment is equal to a constant, shear force will of course be equal to 0. The assumptions in pure bending are: number one, the beam is symmetric about the xy plane. Number two, all loads act in the xy plane. Thirdly, sections originally perpendicular to the longitudinal axis remain plane and perpendicular. And number four, the beam only bends about the z-axis. Some beams are not in pure bending. In fact, most beams are subjected to loads that produce both bending moments and shear forces, which are called non-uniform bending. In these cases, both normal and shear forces are developed in the beam. Normal stresses are calculated using the flexural stress formula. We will now take a look at the distribution of shear stresses associated with the shear force in non-uniform bending. Let us begin by examining a beam of rectangular cross-section. We can reasonably assume that the shear stresses act parallel to the shear force. Let us also assume that the distribution of shear stresses is uniform across the width of the beam. Why don't we take a closer look at the shear stresses? Shear stresses on one side of an element are accompanied by shear stresses of equal magnitude acting on perpendicular faces of an element. Thus, there will be horizontal shear stresses between horizontal layers of the beam, as well as transverse shear stresses on the vertical cross-section. One very important point to remember: at any point within the beam, these complementary shear stresses are equal in magnitude. For the purposes of our discussion, instead of evaluating the vertical shear stresses acting on a cross-section, it is easier to evaluate the horizontal shear stresses acting between layers of the beam. Let's take two adjacent cross-sections at a distance dx apart. The bending moment and shear force acting on the left side will be called M and V, and since the moment and shear force may change along the axis of the beam, the right side will be noted as M plus a change in M and V plus a change in V. Let's perform some hand derivations. Consider a free body diagram of the shaded portion of the beam. From this figure, as you can see, the shear force acting on the horizontal plane, which will be called VH, is equal to tau, the shear stress acting on that plane, times the area that the shear stress acts on, which is T times dx. The resultant of the differential forces integrated over the left end and also the right end of the segment, which shall be called F1 and F2 respectively, may be written as F1 first. F1 is equal to integral sigma dA. And if you recall from your derivation of the flexural stress formula, sigma is equal to negative my over I of the neutral axis. Let's substitute this sigma into the F1 equation. So therefore we have integral negative my over I of the neutral axis dA. Let's put the constants outside of the integral sign. Therefore, we have f1 is equal to negative m, that's a constant, over I of the neutral axis, that's also a constant, times integral y dA. Well, similarly, the resultant of the differential forces integrated over the right end of the segment, which shall be called F2. F2 is also equal to integral sigma dA, and again, sigma is of course going to be replaced with negative my over I of the neutral axis, but of course the sigma of the right segment is different than the sigma of the left segment because the moment of the right segment is not m, but it's m plus dm. So let's replace this. This is equal to integral. The moment is now of the right segment m plus dm y over I of the neutral axis dA. Let's put the constants outside of the integral sign. Therefore, we have F2 is equal to negative m plus dm over I of the neutral axis times integral y dA. The free body diagram is in equilibrium, so therefore if I sum the forces in the x direction, and I'd like my positive to go to the right, that would be equal to negative F1 minus VH plus F2 is equal to 0. At this point, the transverse shear stress formula is just a matter of putting things together and rearranging things where they belong. The summation of forces in the x direction equation, I'd like to rearrange that and write it as VH is equal to F2 minus F1. Well, VH, that was equal to tau times T dx, and F2, that was equal to negative m plus dm over I of the neutral axis times the term integral y dA. And of course F1, that was equal to negative m over I of the neutral axis times integral y dA. The right side of the equation looks a little bit messy, so let's clean it up and factor out integral y dA. As you can see on the right side of the equation, I have negative m and I've got positive m. Of course, they will cancel out. So what I have left is negative dm over I of the neutral axis. I'd like to find the formula for the transverse shear stress in our beam. And I'd like to move dx on the right side of the equation, so I will have negative dm over dx, and I would like to move t also on the right side of the equation, so therefore I have 1 over I of the neutral axis times t, and I have the term integral y dA. If you recall, the relationship between the bending moment and shear stress, dm dx, that is of course equal to v. The term integral y dA, that is what we call the first moment of area, and usually the notation is q. So therefore, the transverse shear stress formula in terms of its absolute value is equal to v times q over I of the neutral axis times t.